there's three different initial states to different, and then below this curve, the H mode will disappear. Then we want to understand that, we can understand the kind of the relation between this r dot r prime, because r is a vector. You can see r is a vector here, r prime is a vector here, and then if they have to equal to 0, then they have to perpendicular to each other. So then we will see that the perpendicular to each other side will be exactly, or not exactly, but very close to the gap here. So then we'll see how it happens. So we have this cartoon picture. So you see that the particle will go to close the gap, then they will have, perpendicular 90 degree of that. Then you go to another gap here, they have another 90 degree of that. So then the system, the Berry phase will be here. So we can see that again. So this is the energy spectrum of initial energy spectrum of final, and that's the gap here. And this is the R effective, and this is the original R and R prime. And you see that if you go over this gap, and then the particle, the effective R will to 0, and this point will destroy the Berry phase, and then you don't get any H modes in the final time. So you see, there's to this point, then it will be 0 because they're perpendicular, and then differently, if you go to this point, you see it will be here. So that's the physics of this system. So I don't want to talk much about how we obtain that, but you just have to know that because the gap will give you different velocity of this R vector. So if one R vector is very slow, one is very large, then they have the chance to be perpendicular. That's the reason. Okay. So the gap will control the gap velocity, group velocity of the system. So therefore, very close to the gap, then the system can have one very slow R vector, one very quick R vector, then they will be perpendicular. But so this is, so at the end I want to see the H state, how this one, how this H state behave. So then the case one is that you always go over the phase boundary, then you see the H state will quickly go to 0, go to a box state. So you don't have any H state remain. So then at the end you don't get any topological system. The topology of the final system is does not exist. For the phase 1 to 1 without dephasing, that means you quench the system in this direction, then you still get non-zero Berry phase at the end, so you still get the phase, the H state. You see the H state won't disappear through the time, and then you have only very small perturbation or small quasi-particle go over, but at the end it will disappear, and then you get H state. So, but the other case is that you have a kind of dephasing even in the same phase. So you see that they will go to box state very quick, same as the situation 1. So okay, so that's how many time we have? 5 minutes. So you want me to stop here?
Well, just
okay. So then I cannot because I'm very slow. But okay, this is the other example how to use local compatibility to distinguish different phases using Quench. This is our recent work, but I don't think I have time of that. So the message is that if you have local compatibility, the local compatibility is that if the two states can be convert each other using LOCC, if you can do that, then you have this entropy larger than 0. And then you can use differential local convertibility. And then the H mode, eventually the H mode can break the local convertibility. That means if you have H mode is kind of very stiff stuff. So they don't like to transform to each other. They don't like the state to have the similarity. The H mode is so different. But if you have overlap, then the overlap can be used as a communication stuff, and then they can communicate with each other. Then you have kind of overlap of that, so you can talk to each other. Then the state can be converted to each other. So that's the message. So if you have overlap here, then the two states can convert to. If you don't have overlap here, the system cannot. And this is our final result. So. The first one is quantum quench or Taiwan system won't be summarized, and recreation of Maurer fermion can happen as effective as non-trivial variables. As effective actually depend on the initial condition and have memory effects. So the local convertibility is broken down through the existence of unpaired Maurer fermions. Okay, thank you for your attention.
So we have time for a couple of questions. So the results for southern quench, what about if I do a quasi-adiabatic type of quench? What kind of things do you expect? Because
we have numerically done that, but for me it's like the work I think interesting because we really have this effective effective for the final state, and then can decide if the variable is 0 or not. And this, for me, is not very easy to be done for the continuous quench, because for the continuous quench you have to the parameters have to be changed in each step. So I don't have any result of that. Maybe I can use some kind of integration of that, but I still don't know. However, we can numerically do that. Okay, numerically is easy. I mean, each step you just separate to each step, and each step you use the same concept. But we don't have analytical result. Also, I'm thinking about that. So I think there is probably a way to integrate all these objects and get effective object, but it's not very clear for me. Here we derive that, really the form, and this I think nobody has done that for this quench problem.
Question from students. I mean, general questions, because this is a very tough subject. Physical realization possible. Can they do this?
For me, the problem is that how to measure the entanglement. That's not some proposal, but still, entanglement is not very easy to measure. I mean,
even very phase is not very easy.
Even very phase, but very phase is also already doable. But the entanglement is kind of proposing state. Okay. One thing I can do, or we can do, is that can you extend that to the Hamiltonian, not for the G? And this for Hamiltonian is very easy to understand for kind of stationary, just the equilibrium property is easy. Okay. For a time dependence case, this is easier because you have G, and you have this correspondence. But for Hamiltonian, it's not very easy. So you really don't have this effective R for the Hamiltonian. I'm thinking how to extend that for the Hamiltonian to write down the effective R, and then numerically you can really propose for the experimental list to do the measurement for the real Hamiltonians, not for the entanglement. But because I'm also like information people, so I'm thinking first about this. But now I'm back to define what is the time-dependent situation for the exact open boundary of topological system. And if we can really find, well, I found some motivation. In fact, we believe that if chain is long enough, they will approach to each other. But still in working stage, so I'm doing that with my postdoc.
No further questions. Let's thank the speaker again. Thank you.